All right, so moving on to sections P7 and P8. This is rational expressions and rational equations. So the first important concept we're going to talk about is called domain. You may or may not have heard of it before. The domain of an expression is just the set of all values at which the expression can be evaluated. The set of values that you can plug in and the expression still makes sense. Okay. So what are like two places in math where you go, oh, we can't do that? Dividing by 0. And what else can we just not do? Square root of a negative number. Or not just square root, but any even root, right? Square root or fourth root or sixth root. Yeah. But there is a way around that, but it's, for right now, we're talking about within the real number system. And our way around that is to leave the real number system. So we're still being consistent. Oh, ignore that, sorry. Okay, so here's a little summary of the different kinds of domain restrictions there are. After we go through the lesson, this will be a nice handy reference, but right now it might look a little overwhelming. But all you really have to remember is you can't put a 0 in a denominator, and you can't put a negative under an even root. Okay. So I want to find the domain for these expressions, right? So the definition of domain, which is the set of all values at which the expression can be evaluated, is a little wordy, but once we do a couple, you're going to be like, oh, that's all it is, right? So here's my expression, x squared minus 9 over x minus 5. What's the only number that I can absolutely not plug in there? 5. Because why? It'll put a 0 in the denominator. So my domain is a set of numbers. It's the set of all numbers that I can put in there. And the way we describe sets, we learned last week. I can use the curly brackets. I could say the set of all x's such that x is not equal to 5. So the set of all x's except 5. If I wanted to write it in interval notation, it would be a little more difficult. I would say, well, I can start at negative infinity, and I can go to 5, right? But not include the 5, because I can't plug 5 in. But I could plug in 4.9 or 4.999 or 4.999999999. And then I would say, okay, I can start at 5 and go to infinity, because I could plug in 5.1 or 5.01 or 5.00001, right? Just not 5 itself, so I just put 5 but don't include it. And then I put a big U between those two to say, put those two sets together. So the U stands for union, like they get married. So there's just two ways to express this. You know, use your favorite, doesn't matter. So for B here, what values can I not plug into the expression? 1 or negative 1, yeah. So I have to say, well, x squared minus 1, I have to make sure that that's not 0. My denominator can't be 0. So then I just solve this thing. X squared then can't be 1, which means that x can't be plus or minus the square root of 1, which is 1. So in set builder notation, the one with the curly brackets, this would say the set of all x such that x does not equal plus or minus 1. And that would be pretty difficult, not difficult, but tedious to write in interval notation. We'd have to have 4 sets of parentheses, so we're just not even going to do it. So for C, any x values that I need to exclude from here, anything that would cause the world to implode, like division by 0 or the square root of a negative number? There's no fractions, right? So that I don't have to worry about zeros and denominators. And there's no roots, so I don't have to worry about taking the root of a negative. So we say that the domain of this guy is all real numbers. For short, I would write I would just write this. Set of all real numbers. The R with the double line stands for the set of real numbers. Or you can leave the curly brackets out. Or if you want to use interval notation, we could say negative infinity to infinity. So those are just all ways of saying the same thing. You can plug in any x value you want. Okay. Now I want to find the domain of these two expressions. I want to know what values of x can I plug into the square root of x plus 3? Yes. Anything greater than 0. Greater than negative 3. Okay, good. So I have to make sure that x plus 3 has to be bigger than 0, right? The whole thing under the radical has to be bigger than 0. Can it equal 0? Yeah, you can take the square root of 0. So bigger than or equal to 0. So then we just solve this inequality, subtract 3 from both sides, and you get x has to be bigger than or equal to negative 3. And then we could easily convert this to set builder notation with a little bracket and just say the set of all x such that x is bigger than or equal to negative 3. In interval notation, I would say negative 3 to infinity. Include the negative 3. And you can always check, right? Pick a number smaller than negative 3, like negative 4. If I plug that in, I end up with a negative 1 under the radical, so it seems to be right. I can't plug in things smaller than negative 3. Yes? You can take the square root of 0. Because negative 3 plus 3 is 0, and the square root of 0 is 0. Yeah, so that's a common, like, because we just spent so much time not letting something be 0, which was the denominator, it's easy to try that transfers. So in B here, I have two restrictions. I have a restriction in the numerator because I have a square root, and a restriction in the denominator, which can't be 0, right? So we have to keep straight what the restrictions are. So in my numerator, I know x minus 2 has to be bigger than or equal to 0, because I can take the square root of anything 0 or larger, which means x has to be bigger than or equal to 2. But then I have another restriction in the denominator where my denominator can't be 0, which means x can't be 5. So I have all the x's bigger than or equal to 2 except for 5, right? So if I wanted to write it in interval notation, I would say I can start at 2 and include it, go up to 5, but I have to skip over the 5. Can't actually include the 5. So I could go to 4.9, 4.99. So I'm going to write 5, but don't include it. And I indicate skip over the 5 by marrying it to another set that starts at 5 but doesn't include it and goes to infinity. In set builder, I would do the set of all x such that x is bigger than or equal to 2 and x is not 5. So the whole gist of domain is exclude any x values that would make your denominator 0 or would force you to take a even root of a negative number. Okay so far? Okay. Okay, so we're going to do some work with rational expressions, which is just fractions with variables in them, right? So in order to be able to do it with letters, we need to look really closely at how we do it with numbers so that we can do something similar. We can expand what we do with numbers to what we do in a more complicated situation. So if I want to reduce the fraction 12/15, how do I do that? Divide the top and bottom by 3. So why am I allowed to do that? What am I really doing here? Factoring, yes. So I'm going to write each number as its in factored form. So 12 I could write as 3 times 4, and 15 I could write as 3 times 5. And that's why dividing by 3 works. Because really what I'm doing is canceling a 3 that's in the top and the bottom. So this reduces to 4/5. So the whole premise behind what we do when we reduce a fraction is factoring. Factor it as much as you can, cancel anything that the top and bottom has in common. Okay, so I want to reduce the fraction and then find its domain. So x squared plus 3x minus 10 over x squared plus 2x minus 8. So the idea behind reducing is factoring first, right? Factor and cancel. So x squared plus 3x plus 10, does that factor? Minus 10. So I need numbers that multiply to 10 and add to 3. 2 and 5 where the 5 is positive. Yep, that works. And then we got to factor the denominator. Yep, x plus 4 and x minus 2. And lo and behold, we have a common factor, right? We have an x minus 2 in the top and the bottom. They cancel. And my reduced expression is x plus 5 over x minus 4. Yeah, thank you, sorry. The domain is all numbers except -4, and what else can we not plug into the original expression? You can't plug in a 2 either into the original one. So this expression and this expression are completely the same, right? They're equal, except for the fact that in this one I can't put in -4 or 2. This one I can put in a 2. So in order to make these two continue to be equal, I have to restrict the domain. So the domain here is set of all x such that x can't be -4 and x can't be 2. So they want you to reduce the expression and find the expression's domain. So just think of it as finding the domain of the original expression. Okay, and the reduced one is going to have the same domain. So x plus 8 over x plus 4. You can't do anything. Those are both completely factored already. So this is already reduced. It's in lowest terms. There's no factoring that can be done so that there's nothing to cancel. What's the domain? Yep, set of all x except -4. Right. Because they asked me about this expression. They said reduce it and find its domain. So the domain of this expression, because once I factor it, I can't plug in a -4 or a 2. Either one would make the denominator 0. Correct, but yes, after I've reduced it. But this is the expression they asked me about. They want me to find the domain of this guy. And if I try to plug a 2 in here, plug a 2 into x squared plus 2x minus 8, you get 0. Yes, you got it. Okay, so operations on rational expressions, just like operations on fractions, just now we have letters, variables, unknowns. So if I want to divide two fractions, what's my rule for dividing fractions? Flip and multiply. Flip the second one and multiply them together. So I'm going to x squared minus 25 over x squared minus 16 times the reciprocal of the second fraction. So this would be x plus 4 over x squared plus 6x plus 5. Now, if I just, what's the rule for multiplying fractions? How do you multiply two fractions together? Straight across. Multiply the tops, multiply the bottoms, right? However, this is going to get a little messy, particularly the denominators, right? They're kind of big. I would rather not multiply them. So if I can, I'd like to cancel first. Anything that can cancel. So let's factor everything out and see what cancels. So x squared minus 25 factors to x plus 5, x minus 5. X squared minus 16 factors to x plus 4, x minus 4. Then I have an x plus 4 on top over here. And x squared plus 6x plus 5 is going to factor to x plus 5, x plus 1. And I have lots of common factors, right? So I can cancel. I have an x plus 4 in the top and in the bottom, so they get to cancel. I have an x plus 5, one on top, one on bottom, so they cancel. And then I can write out my final product. In my numerator, I'm left with an x minus 5. And in my denominator, I just have x minus 4 times x plus 1. And if you multiplied these two together, if you went one step further and FOILed the denominator, that'd be perfectly acceptable. Also would be a correct answer. Questions so far? All right, so let's look at part B here, where I'm going to subtract two fractions. So what's the general rule when you're going to add or subtract two fractions? You need a common denominator. Okay, so a common denominator, how do we normally find it? You can multiply them together. That's one way to get a common denominator, because that would be a common multiple of the two fractions. What's what do we call it when you get the smallest one? The least common multiple or the lowest common multiple. And we do that by factoring, right? Let's look at a quick example. If I did Okay, say I want to do 2/5 plus 1/15. I could multiply them together. 15 times 5 is 75. So I could get a common denominator of 75. But I could get a smaller one, right? Which would be what? 15, yeah. So the way I do this is the way we come up with 15 sort of in the formal methodology is we rewrite 15 in totally factored form. You rewrite every denominator in totally factored form. And then you say, okay, to make them look alike, this one needs a 3. So I multiply by 3/3. And this one needs nothing, so I just leave it. And then they have a common denominator. Let's do another one where I have 3/10 plus 6 over 42. I don't know, just made it up. Okay. So the way we get a common denominator, which everybody has a way to do this in their head much faster, but I'm just reminding you of what it is that you're taking a shortcut to do, because we're going to have to do it with letters. So we rewrite the 10 as 5 times 2. And we rewrite the 42 as what? 6 times 7 or 3 times 2 times 7. If we write it in totally factored form, prime factorization. So to make them the same, they both already have a 2, right? This one needs a 3 and a 7. So you multiply by 3 and 7. And this one already has a 2. It needs a 5. So multiply top and bottom by 5. And then the denominators will be the same. 7 times 3 times 2 times 5, whatever that is. Is this coming back a little bit? I know that this is more formal, like you often do this much faster in your head, but when we try to do it with these variables, it's helpful to have this to refer to. So the step 1 in finding a common denominator is totally factor everything. Okay, so we're going to have x over x plus 2 times x plus 1. Oh, sorry, I didn't see that minus. Yeah, minus 1. Minus 2 over, yeah, x minus 4 and x minus 1. Good. So to make the denominators the same, they both already have an x minus 1. I want them to be the same, so I don't have to add that to either one. So in this one, I could do multiply by x plus 2 over x plus 2. And then it has all 3 factors, a minus 4, a minus 1, and a plus 2. And then this one is just missing the x minus 4. So I would multiply by x minus 4 over x minus 4. And then they'll have the same denominator. So x minus 4 times x gives me x squared minus 4x. I wrote CD for common denominator because I don't want to write all those out over and over again. I'll write them at the end. And then 2 times x plus 2 is 2x plus 4 over the common denominator. Now I just have to do the subtraction. So this is x squared minus 4x minus 2x plus 4, right? That's the rule when you have fractions. Just subtract the tops. Keep the denominator the same. So I distribute the negative, combine like terms, and I have x squared minus 6x minus 4 over the common denominator, which was x minus 4, x plus 2, x minus 1. Okay. So the idea behind solving equations that have fractions in them is to get rid of those horrible, evil denominators, right? We just would like them so badly to be gone. Because whenever you see a fraction, you go, ugh, right? But we have a nice, easy, we can just get rid of them anytime we want. Because one of the rules about solving equations is you can do anything as long as you do the same thing to both sides, right? So whatever you have in the denominator, multiply both sides by that, and it'll cancel out. So I look at this equation right here, and I say, okay, I have an x in that denominator. I just wish there was no x there. If there was no fraction, this would be so much easier. So I want to get rid of it. I want that x to be gone. So to get rid of it, I multiply both sides of the equation by x, by the denominator. Now I have to distribute this x to both terms here, and I get x times 1 is x. And what is x times 1 over x? 1. This is an x in the numerator, this is an x in the denominator, they cancel. And I just get 1. Hooray, the fraction's gone, right? And then I have x times x, which is x squared. And now I have a quadratic. Now I have a quadratic, which I have the tools to solve, right? I can use the quadratic formula. I could factor. So if I used the quadratic formula, I would say x squared minus x minus 1 is 0. Solve it using the quadratic formula. Which we don't have to do now. But the solution to that equation is called the golden ratio. It's a really famous number. You see it in nature, you see it in art and architecture. It's really kind of cool. If you ever are interested, you should look it up. Google it. There's tons of info. Okay, so if we look at B, now I have lots of fractions. Oh my God, right? Oh, I wish they were gone. I wish they were gone. So I'm just going to work my way through getting rid of one denominator at a time. So I look at this first one. I have an x plus 1. Wish it was gone, right? How do I get rid of a denominator? Multiply by it, yeah. So I'm going to multiply both sides of this equation by x plus 1. And when you multiply by something, you can always write it over 1, right? So I just wrote that to remind myself that the x plus 1's in the numerator that I'm multiplying by. Okay, so I distribute. What is x plus 1 over 1 times 1 over x plus 1? 1. 1 in the numerator, 1 in the denominator, they cancel. Okay, now I have to multiply by, distribute the x plus 1 to the other term. And when you multiply fractions, you multiply the tops, multiply the bottoms. So this one is going to be x plus 1 over x minus 4. Do x plus 1 times 1, and the 1 times the x minus 4, that's the resulting fraction. And then on the right, I have an x plus 1 in the numerator, x plus 1 in the denominator. They cancel. So I'm left with x over x minus 4. So I've won a third of the battle, right? I've gotten rid of one of my fractions. One of them is gone. So I still have an x minus 4 in the denominator here. To get rid of things in denominators, multiply by them. So I'm going to multiply both sides of this equation by x minus 4. X minus 4 times 1 is x minus 4, right? Anything times 1 is itself. And then when I distribute this x minus 4 to the next two terms, it's just x plus 1 because I have an x minus 4 in the numerator and the denominator. They cancel. So I just have x plus 1 equals x, right? The x minus 4s cancel on the right. And now this is a super easy linear equation. Combine like terms, so I have 2x minus 3 equals x. X equals 3. Now, if you've seen this technique before, you don't have to eliminate the denominators one at a time. You can do them all at once. So I could have multiplied by x plus 1 and x minus 4 in the same step. So if you are used to that, or that just makes more sense to you, go ahead and do that. Okay, so I'm going to let you try C in your groups. I want you to try to solve this equation.